Hello again. Here is the third of our harder circular motion questions. I've picked this one because it's such a short question, and you'd think that it was the longer questions that were harder, but actually it's often ones like this which are just one or two sentences long, and particularly ones without a diagram that students find hardest to do. We have to try and read this, understand exactly which words are important, which ones aren't, and try to get a sense for the geometry of the situation. Um, and we also have to try and decide how to actually go about drawing this and what we need to calculate. So, as we're reading through this, there are some words that jump out straight away. There is a particle which is moving with constant speed in a horizontal circle. So I know it's going to be a horizontal circular motion question. They've given us the radius of the circle, and they've told us that it's moving inside a fixed, smooth, hollow sphere. And they've also told us the radius of the sphere, and we've got to show that something is true. This is the second way in which this type of question is hard for people. There is no clue given in the question about how this equation is going to magically jump out of the algebra. We're going to have to trust that we can set up the situation, create some equations, manipulate them, and magically get the answer we require. Now there's one big secret for doing any sort of question like this where it's going in a horizontal circle around the inside of a sphere, and that's this. It is just a banked curve. We've solved quite a lot of questions involving cars, and other objects going around banked curves. They're actually very simple questions. There's only two forces acting on them. There's the force due to gravity acting vertically downwards, and then the normal reaction, which is the force that provides the circular motion. It's exactly the same in this case. The only issue is we need to be able to work out what the angle of banking is. Because it's a sphere, the angle changes continuously depending on where exactly on the sphere you are. So we're going to need to figure out the geometry of the situation so that we can figure out exactly what angle the normal reaction is going. So this is what the geometry looks like. We've got a sphere of radius 2a. We've been told the radius of the horizontal circle, which is 3 over 2a. The angle we need is the angle marked on the diagram. And it's actually not too bad because that's a right angle triangle. We can work out all of this just using Pythagoras, and we're getting quite good at that. Well, Pythagoras and basic trigonometry. And if we do that, it's relatively easy actually just looking at that to see that we can work out the cosine straight away. The cosine is the adjacent divided by the hypotenuse. Once we've got that, the fact that it's a 3, 4, it's not a 3, 4, 5 triangle sadly, but it's a 3, 4 something triangle, we can work out the missing length by doing the square root of 4 squared take away 3 squared. That's the square root of 7. And so it's quite easy to see that we get the sine being root 7 over 4 and the tan being root 7 over 3. If you're not happy by doing it geometrically, there are quite nice algebraic relationships between cosine, sine and tan, and we need to be confident at moving from one to the other at this level of mechanics. Okay, so now we've got that, we can draw the force diagram. And as we've been saying with previous questions, it's the force diagram which is the key to solving every mechanics question like this. If we get the diagram right, everything is simple. If we get the diagram wrong, the whole thing falls apart. So let's have a think about what the diagram would be. We've only got, as I said, two forces. We've got mg vertically downwards, and we've got the normal reaction at a certain angle. And we've already worked out what the cosine, the sine, and the tangent of that angle are. The other thing to add to the diagram is the acceleration due to circular motion. Now, I reckon it's going to be something to do with v squared over r, and that's because in the question they tell us that it's moving with a constant speed u. And remember, we always either use v squared over r or omega squared r. So the acceleration due to circular motion is v squared over r v squared is actually u squared in this case, r is 3 over 2, so we get this relatively nice expression for the acceleration due to circular motion. Okay, so let's just pause a second. We've got a force diagram. We have several unknowns there. We don't know r, we don't know the mass of the object. We've got a formula that we've got to try and come up with, an equation we've got to try and come up with, and it doesn't have r in and it doesn't have m in. Somehow we're going to have to try to find some formulae or some equations and eliminate r and m. So we're not sure what's going to happen, but whenever we've got a situation like this, we know two equations that we can always calculate. We can always resolve horizontally and resolve vertically. So if we're not sure what to do, let's do that and let's see what happens. I've resolved horizontally and I've resolved vertically. Resolving vertically is very easy. We've got the vertical component of the normal reaction, which is r sine theta, and that's equal to mg. Excellent. If we resolve horizontally, we've got the horizontal component of the normal reaction, r cos theta, and we've got, by Newton's second law, mass times acceleration. So it's a good point here to pause, look at what we've got, and look at what we want. And remember, it's this thing up here in the question that's our goal. We want to have a, we want to have g, we want to have u squared, and we need these other numbers as well. Now there's certainly some of those things appearing here. There's a u squared in the second equation. There's an a in the second equation as well. There's a g in the first equation. What we need to get rid of is the r and the m. Now a lot of people are comfortable with simultaneous equations, with elimination by adding, elimination by subtracting or scaling, and a combination of those. There's often a way of combining these, though, that people miss, and that's you are perfectly allowed to divide one equation by the other. And this is what we need to do in this case, because if we divide equation 1 by equation 2, both the left-hand sides have an r, and that's going to disappear. Both the right-hand sides have an m, and that's going to disappear. So by doing that, we eliminate the two things that are causing us a problem in one go. The r disappears, the m disappears, sine theta and cos theta are going to turn into tan theta, and we already know what tan theta is, it's up there. And we should, hopefully, get something that's very close to what we want. Let's see what happens. So we divide the first equation by the second equation, we get tan theta is equal to, delete all the m's, 3ag over 2u squared. This is looking good actually, because remember we do know what tan theta is. We know tan theta is root 7 over 3. That's one of the things we worked out when we were thinking about geometry. So if we substitute that now and rearrange, let's see what happens. We got root 7 over 3 is 3ag over 2u squared. All we have to do is cross multiply and simplify everything, and we've magically got exactly the equation that we were asked for. And that's it. Some people get a little bit unsatisfied by questions like this. They think, well, I haven't really done enough. I haven't come up with a nice answer. It's not saying that it's moving at 10 meters per second or taking 6 seconds. But we need to get happy with getting to a stage like this and just saying, we're done. You know, this is all the question was asking us to do. That is it. Let's have a quick summary of what this question involved then. As with all of these questions, they can initially look very, very complicated, but it is just a banked curve problem. So whenever you see a question that involves going in a horizontal circle around the inside of a sphere, we need to try and figure out what the angle is that the normal reaction is going at. That comes from geometry. With this question, as with the previous two, we had to resolve vertically and we resolve horizontally. Pretty much every question involving a horizontal circle is going to involve us doing these two things at one point or another. It should almost be the very, very first thing that you think about doing. Once we got those two equations, we needed to try and think about how to get the equation that the question actually wanted us to do. And in this case, that came from dividing the first equation by the second. And as I've said, we need to be happy at a further maths level with having equations that have surds in, that have unknowns in. It's very easy to think that you've always just got to come up with a number, but this is the solution they are looking for. And as I've already talked about in previous questions, if we just look at the layout of my solution, I've highlighted answers, I've explained what I'm doing. I'm not just magically making equations appear out of nowhere, so if I'm resolving, I tell you the direction I'm resolving in. It's little things like this that help the reader, the examiner, the teacher, other students understand what you're doing. Even yourself, if you're doing a question, then coming back to revise at a later point. These questions, which initially look really nasty and look like you're not going to have any idea how to do them, become very, very simple if you just follow the same steps as you do with any other circular motion. Thank you.